Hi everyone, we are starting the session that is on physics paper 1, the MOKASA. Join, share the link to your friends so that they can also join. We start it together. We are starting by looking at question number 1. We are starting by looking at question number 1. A student measured the diameter of a nichrome wire as 0.36 millimeters. On the space provided, draw the micrometer screw scale reading 2 marks. With that question, learners, this is how we have to draw. In order to draw it, we need to have the sleeve scale and the thimble scale. That's how we get the marking. So let us have the drawing. Let's have the drawing. Let's have the drawing with us. Let's have our drawing. This is our drawing over the same. We are giving the drawing over the same. Let me give you a drawing. That is 40 because it is 0.36, so 39, 38, 35, 39, 38, 39, 38, 37, 36. Then I might have 35 slightly there. This is, that is 35. Then with the sum here, let's have it and so we see what we could have done there. So because it should be like that, then we need another one at here, 36 exactly, so that it goes like that. Then this one here, the value is 0. It's a 0. So learners, when you look at that, it is now 0.36. So with your sleeve scale and the thimble scale, when you have it, it's very clear. So now you can see the reading on that one is 0.36. Question number 2. The diagram below shows a wire loop with a thread tied across it. The loop is dipped into soap solution such that the soap film covers it as shown. Region X is punctured on the space alongside the diagram. Sketch this resulting shape of the wire loop. Give a reason for the shape. So if we are having it like that, and we tend to puncture point X, let's see what happens. Let's see what happens when we puncture the point X. Let's see what happens upon puncturing the point X. Upon puncturing that point X, it's going to form for us something more like a circle. Form for us something more like a circle. Oh, sorry. It's going to form for us a circular something of that sort. Yes, so that is how we expect it to behave after it has been punctured. Give a reason for the shape. So you see that upon puncturing, the surface tension at that point becomes lowered. Once the surface tension at point X becomes lowered, the surface tension at the extents of that thread will become greater. Therefore, it will be pulling the thread and resulting into it forming such a figure. So how are we going to put our point? So we are going to say the surface tension is greater. We are going to say surface tension surface tension is greater. Surface tension is greater all round. The surface tension is greater all round the thread. The surface tension is greater all around the thread, pulling. The surface tension is greater all around the thread, pulling it radially. Pulling it radially. Pulling it radially due to outward. Pulling it radially due to outward resultant force. Resultant force. So learners, what you learn, upon puncturing point X, the surface tension at that point becomes lowered. Once the surface tension at that point becomes lowered, the surface tension at the extents of the thread become greater, thus pulling the thread, forming something like a circle, pulling it radially outwards. As a result of that, we obtain the figure as we've seen. Question number, part B of the question. Part B of the question, learners. Diana placed her finger on the surface of water. Diana placed her finger on the surface as shown in the diagram. Name the force. Name the force that lifts water. Now, when we look at it, learners, water is in contact with the finger, and once someone is trying to move the finger, we are seeing it water being stuck there. So this force is the force we call adhesive force, a force of attraction between molecules of different kinds. The molecules in the finger and that of the water are different, but now because they are in contact, meaning the adhesive force is greater. So the force involved there is what we call adhesive force. Adhesive force. Adhesive force. So that force is called adhesive force. The force is called adhesive. Why is it adhesive? Because it is a force of attraction between molecules of different kinds. Question number next. The diagram below shows a cuboid with dimensions 20 centimeters by 20 centimeters by 40 centimeters of mass 5 kg. State and explain how it should be placed on the surface in order to exert minimum pressure. State and explain how it should be placed on the surface in order to exert minimum pressure. This is, learners, this is a pressure on solids. Remember, when we are told to calculate pressure in a solid, we normally say pressure is given by force over area. Pressure is normally being given by force over area. If you look at the relationship, learners, between pressure and area, they are inversely proportional. Now, because we want to get to exert minimum pressure, it means when for pressure, our area must be maximum. For pressure to be minimum, our area must be maximum. How will we achieve that, dear learners? So, remember that how should it be placed on a flat surface? We need to go with realities here. So, we need to place this cuboid on a flat surface such that the side with the bigger dimensions, remember that the bigger the dimensions, the bigger the area. So the side with the bigger dimensions should be in contact with the surface. So we'll say, in order to get the 2 marks, place the cuboid. This is how we'll frame our answer here. Place the cuboid with bigger dimensions. Here are 40 centimeters, with 40 centimeters by 20 centimeters, with 20 centimeters by 20 centimeters face or side, that side that has these dimensions, on a flat surface, on the flat surface. This ensures maximum area of contact. This ensures maximum area of contact, hence minimum pressure, hence exerting minimum pressure. So learners, what is very important for you in that case, you need to know that you place these parts, because these ones here will provide you a larger area that will provide a maximum area of contact. These are our key points. So when the maximum area of contact is provided to the surface, will now be having being exerted, less pressure being exerted. Question number next. Explain the formation of steam at 100 degrees Celsius using the particulate nature of matter. Explain the formation of steam at 100 degrees Celsius using the particulate nature of matter. So we say the intermolecular distances between the liquid molecules increases. Intermolecular distances intermolecular distance between liquid molecules between liquid molecules increases weakening cohesive forces weakening cohesive forces of attraction. Now, learners, remember, at 100 degrees Celsius, temperature is very high. Particles are vibrating so fast. The vibration of the particles weakens the cohesive forces. Once the cohesive forces get weakened, then we can experience formation of steam. We can easily experience now formation of steam. We are going to the next question. If you have a question, please make sure to drop it in the comment section so that I can see where you need help and how I can give the help. Sorry for that. And how I can give the help. The figure below shows a simple bimetallic strip used to detect fire. So we have the bimetallic strip, made up of two metals, that is iron and brass. We have the contact point, we have the siren, we have the switch. Describe how the fire alarm works, learners. You know that with our bimetallic strip, the two metals, one metal has to expand more than the other, and obviously it is brass expanding more. And it's being connected, because it's used to detect fire, then it's connected to some source of heat. So we simply say, what we know is that when the temperature rises, the bimetallic strip will expand, with brass expanding more than iron. That will make the bimetallic strip to bend or to curve downwards, making contact. That will make it to curve or bend downwards, making contact. So how are we going to frame our answer, learners? We are going to say, when temperature rises, when temperature rises, the metal expands. The bimetallic, let me be specific, the bimetallic metals expand at different rates. They expand at different rates. Brass expands more than iron. We know always that brass expands more than iron. Brass expands more than iron, causing the strip to bend. Brass expands more than iron, causing the strip to bend downwards. Making contact. Making contact. So you see, once the temperature rises, the metals in the bimetallic strip expands at different rates. Brass, being that it expands more than iron, it will curve downwards. Once it curves downwards, you'll see it making contact with the contact point. So that is how it works. Jane stirred hot tea using a metal spoon and observed that the handle of the spoon soon becomes warm. State two ways through which the heat is conducted to reach the hand. One way is by use of free electrons. Solids have got free electrons. So we can talk about use of free electrons in solids. Those ones, someone else can talk about mobile electrons or delocalized electrons, whichever the case. Another thing, because the hot tea will make the spoon become also hot, and there will be vibration of particles. Now those particles are there as they are not particles, but let me talk about atoms. When those atoms are vibrating, they'll transfer the heat until when it reaches hand. So another way is by vibration of atoms. Vibration of atoms or particles. Vibration of atoms or particles. Vibration of atoms or particles. Question number next. The diagram below shows a uniform metal bar of mass 150 grams. Mass 150 grams placed horizontally by a force F. Determine the value of F. Determine the value of force F. This is we're going to apply the principle of moments, that for a system in equilibrium, the sum of clockwise moments about a point must be equal to the sum of anti-clockwise moment about the same point. We've been told it's a uniform metal bar. At the end, you're being balanced by a force F. So let's see how we will answer the question. The diagram below shows that. So the total length of this metal bar is if you look at from here to here is 125, from here to here is 75. So the total length is 75 plus 125, then it means it is 200 centimeters. That's the total length of the bar. Then we have the COG. The COG acts at the center. So at some point here, I'm expecting some weight here. Sorry. I'm expecting some weight here. I'm expecting some weight. The weight will be acting here. I don't know what is the value. We are going to figure out. The diagram below shows a uniform metal bar of this mass. So meaning this is the mass, we can easily compute the weight. Remember that we know the relationship between weight and mass, whereby we said weight is equals to mg. Therefore, it means the mass is 150. In its SI unit, you divide it by 1,000 to convert it to kilogram. So that will be 0.15 times 10, meaning that the weight of this is 1.5 newtons. So the weight here is 1.5. Now weight is as a result of the force of gravity, therefore it's always directed downwards. Determine the value of the force F. So learners, remember that this upper where there is weight acts at the center, because this one is 200, so it means this point here is 100 centimeters. Then from the pivot to where my weight is, this distance here, learners, will be remember that the whole of this is 100, sorry, is 100, and from here to here is 75. Then it means this point here is 25. That's how we need to break it down. Based on the principle of moments, we know that F1 D1 should be equals to F2 D2 from the principle of moments. So if my F1 becomes the weight, which is 1.5, times its perpendicular distance from the point of support. The pivot is here, so the distance from where the weight is acting to the pivot is 25 centimeters. But remember, it's normally advisable to deal with your calculations in SI unit, so it will be times 0.25. I've just converted that to meters. Should now be equal to F2, which is the force acting on the other side, which is my F, times the distance from the point of support. 75 centimeters is just like saying 0.75. So that tells us F is obtained by saying 1.5 times 0.25 all over 0.75. When you do that computation, learners, you are going to get the value of F as 0.5 newtons. F is 0.5 newtons. Calculate the reaction force. Now, learners, for us to get the reaction force on this pivot, remember we normally have two conditions for a system to be in equilibrium. One, the sum of clockwise moments about a point must be equal to the sum of anti-clockwise moment about the same point. Normally say the sum of upward forces must be equal to the sum of downward forces. In some books, you'll find them paraphrasing that as the sum of forces in one direction should be equal to the sum of forces in the opposite direction. Having said that, when they talk about action and reaction force, action force is the one we exert downwards. The reaction force is the one that goes upwards. That one, hope you learners know better. You need to be aware of that. So having said that, you know, reaction force, in our case, I'm talking about reaction forces are the upward forces. The summation of these upward forces should be equal to action force. Action force is what we call summation of downward forces. Summation of downward forces. What do I mean when I say like that? If you look at your diagram, let me make it clear. If you look at your diagram, learners, do we have upward forces here? We don't have. Allow, we call it, let's just maintain reaction should be equal to the sum of downward forces. When you look at the summation of your downward forces, we have two forces acting downwards. One is the weight of the block itself, the weight of the metal bar itself. So that is 1.5 plus this other force F. It's also a downward force because it's moving down. So plus 0.5. When you do that addition, you're going to get 2 newtons. Because downwards we are having 2 newtons, it means for this object, for this metal bar, it is also experiencing upward forces of the same value, which is 2 newtons, and that becomes your reaction force, dear learners. That becomes your reaction force, 2 newtons. Unless you have a question. Question number 3. Sorry, not number 3, but question number 8. Question number 8. The diagram below shows an arrangement of 2 identical light springs. Each spring has a length of 5 centimeters when unstretched. The total length of the 2 springs is 15 centimeters when supporting a load of 2 newtons. Now these are question learners from Hooke's law, which states that for a helical spring or any other elastic material, extension is directly proportional to the applied force, provided that the elastic limit is not exceeded. And anytime you get that question, think of it as force is directly proportional to extension. F is equals to KE. Let's see. Let's see how we'll answer that question. They are saying that the diagram below shows an arrangement of 2 identical springs. Each spring has a length of 5 centimeters. Each spring has a length of 5 centimeters when unstretched, if not stretched. The total length of the 2 springs is 15 centimeters when loaded with this load. So if it is unstretched, I want to get it from this point. While it's unstretched, when it is unstretched, you realize spring K1 has 5 centimeters, another spring has another 5. So the total extension, if it is unstretched, is 10 newtons. That is the total length when it is unstretched. But when loaded, when now stretched with a load, its length becomes 15 centimeters. Sorry, these were centimeters, not newtons. These were centimeters here. So it means that our load is bringing some extension. Our load is bring some extension. So let's get the total extension that has been caused by the load. The total extension, how do you compute the total extension? Is the total length when stretched, 15, minus the total length when not loaded or when unstretched, which is 10. So you realize, learners, the total extension here is 5 centimeters. Now, because these 2 springs are arranged in series, we need to calculate what? The extension on each spring. Simply, you take the total extension, you divide by the number of springs. So, to get your extension, you take the total extension, which is 5. You divide it by the number of springs that amount to that total extension. In our case, we have 2 springs. So, this gives you 2.5. This is the extension per string. Then the combined spring constant. To get the combined spring constant, learners, to get the combined spring constant, remember, from this what I've written here, F is equals to KE. From F is equals to KE, then it means K, which is our constant, can be obtained by saying force over extension. Then if that is the case, that K is equals to F over E, then it means simply means the load is 2 newtons, or rather even this one we can just take the combined spring constant. What is the total extension? The total, or rather let's just have it split. So the load here, remember, is 2 newtons sharper. This one here is 2 newtons. So spring 1 is supporting a force of 2 divided by its spring constant, which, sorry, with its extension, which is 2.5. When you compute that, you're going to get 0.8 Newton per centimeter. Newton per centimeter. Now to get the total combined spring constant, we normally take the spring constant divided by the number of springs, which is 2. So that is 0.8 divided by 2. This gives you 0.4 newtons per centimeter. That is the combined spring constant. That's a combined spring constant. After computing the combined spring constant, learners, we go to the next one. The diagram below shows moving in the direction shown in air at a high velocity. State and explain the direction of force acting on this. We have it's an aerofoil. Obviously, with the force, we have an upward force. We'll have a force here that is taking it up. Then from here also we have another force taking it up again. And if the streamlines are moving this side, then the movement should be on the opposite side, like that. This is an aerofoil. Then how date and explain the direction of the forces I've stated. Then I'm now going to give the explanation. Learners, we know that in this case, the velocity of the air above the aerofoil is higher. Therefore, it will create a region of lower pressure at the top, while the velocity of the air at the bottom here is lower. So here, velocity is lower. Velocity is slower down here, then pressure is higher. At the top here, the air moving here is moving at a very high velocity. So high velocity at the top here, but lower pressure. Lower pressure. When you compare the two pressures, there is a difference. That difference in the pressures is now what is responsible is aerofoil, hence moving. So how are we going to put our points? We'll say velocity of air is higher above the aerofoil. We're going to say velocity of air is higher above the aerofoil, reducing the pressure. Reducing pressure at that point. At that point or region. Velocity of air below is lower. Velocity of air below is lower, hence higher pressure. Hence higher pressure at that point. Hence higher pressure at that point. The pressure difference the pressure difference. The pressure difference causes the dynamic lift. Always the pressure difference causes the dynamic lift of the aerofoil. The dynamic lift of the aerofoil. Question number 10. The diagram below shows variation of force acting on an object over a distance of 20 meters. Calculate the total work done. Now learners, this is a graph of force against distance, and when you take force times distance, the product gives you work. Remember that when you defined work, you defined work as the product of force and the distance covered. So it means when I take force times the distance, it will be giving me the work done. Therefore, when I'm told to get the total work done, it means this is simply just the area under the graph. So this is equivalent to area. Total work done is equals to the area, the graph. When you look at your graphs well, we might have two figures. Allow I call this one figure A, this one here figure B. If you look at figure A, it is triangular in shape, so its area is obtained by saying a half. So normally a half times the base. The base is from 0 to 10, so times 10 times its height. The perpendicular height is the same as this one here, which is 10, plus, look at my figure B. You look at your figure B, it's also triangular, so it's a half, times the base. From 10 to 20, the difference is 10, times the perpendicular height, that is from 0 to 10, it's 10. Don't worry about that negative. The negative just shows that that part is below the x-axis, so just negate it. So this is a half times this is 50 plus 50, 50 plus 50, 100. It's work done, so you can talk of it as 100 joules. The SI unit of the work done. The SI unit of the work done. So that's how you are to answer that. Section B. The setup below shows a ticker timer used to determine the acceleration due to gravity of at Moi Girls High School, Eldoret. We have the ticker tape, the ticker timer, the retort stand, and the 100-gram mass. Briefly describe how the setup can be used to determine the value of acceleration due to gravity at the school. We need to give the description. So first thing, when you look at this ticker timer, we need to switch on the ticker timer and let the mass fall freely. That should be step number 1. Switch on the ticker timer. Switch on the ticker timer and let the mass fall freely. That should be our first step. We switch on the ticker timer and let the mass fall freely. Step number 2, dear learners, we are going to remove the paper tape and cut it into appropriate number of ticks. We are going remove the paper tape and cut it into and cut it into appropriate number of ticks. Removing the paper tape and cutting it into appropriate number of ticks. That should be procedure 2.